All right, now let's move on to the next topic, model evaluation. So far we have talked about some metrics to compare or evaluate models. We talked about accuracy um, or misclassification rates. They are kind of like complement. Misclassification error rate is equal to 1 minus accuracy. We can also calculate a confusion matrix, or we can calculate conditional accuracy for each class, etc. So, however, for classification models, so far, all the models we have talked about, we always use zero point 0.5 as the threshold for predicted probability. Right? If p hat is greater than 0.5, then y hat is equal to 1. Otherwise, y hat is equal to 0. So we always use 0.5. However, in practice or in the real world, it might not be a good threshold. For example, in very imbalanced data. So suppose the data set is very imbalanced. We have, for example, we have 80% 0 and 20% 1. Then if the predicted probability is 0.6, we may say y hat should be equal to 1. However, in this scenario, probably we should choose a threshold that is close to 80%. If the predicted probability is greater than 80%, y hat is equal to 1 because there are only 20% of 1, right? Instead of 50% of 1. If you choose 0.5 as a threshold, you assume that in the training set we have 50% of 0, 50% of 1. Right? So in order to resolve this issue, people invented this metric called ROC curve, a receiver operating characteristic curve. So this curve will consider all of the possible thresholds for p hat, namely from 0 to 1. Consider all of the thresholds and evaluate the performance of the model for all of these possible thresholds. Right? Use different thresholds to do the rounding, to predict y hat, the value of y hat. And it graphically displays the trade-off between sensitivity and specificity. So two new terms. What is sensitivity? Sensitivity is probability if y hat is positive given y is positive. Right? So this is a probability of making a correct prediction if y is positive. Right? It's also called the true positive rate. True positive rate, sensitivity. And another term is specificity. This is the true negative rate. The probability of making a correct prediction if y is negative is also a conditional probability. It's called true negative rate. And ideally, our model will yield a high true positive rate and a high true negative rate at the same time. Right? They both approach 100%. That is the ideal case. However, in practice, it never happens because there is a trade-off between these two metrics. Right? They always move in the opposite direction. Right? So model has a good combination of them would be considered the best. And the ROC curve sort of plot them, but not exactly. It actually plot it's a line or it's a plot about true positive rate and false positive rate. What is a false positive rate? Is equal to p of plus given negative. Namely, is probability of y hat is positive given y is negative. Right? Because the actual status is negative and the model predict positive. So that's why it's called false positive rate. false positive rate. And turns out it's equal to 1 minus the true negative rate. Fix the condition should be the same. Right? It's 1 minus the true negative rate. Okay, so let's use this area. This area is bigger. Right? Let me draw an ROC curve. I'll try to illustrate true positive rate and false positive rate. Let me clearly notice this is probability of positive given positive. Predicted is positive given true positive. False positive is probability of positive given negative. And is equal to 1 minus true negative rate. Okay, here. All right. Now let's consider a few cases. Consider the threshold. First, theta is, let's call it theta. Okay. Theta is a threshold. It's between 0 and 1, right? Because it's threshold for probability, so it must be between 0 and 1. Consider theta equals 0 case. So when theta is equal to 0, that means given any new observation, you will always predict positive because the predicted probability p hat must be greater than theta. Is always greater than or equal to theta. So your y hat is always positive. And no matter what the feature variable values are, you always predict positive. So this is one extreme case, right? So in this case, probability of positive is equal to 1 always. Consequently, probability of positive given positive is also equal to 1. Right? And probability of positive given negative is also equal to 1. Is that right? Because no matter what, it's always equal to 1. Right? So true positive rate is 1. And false positive rate is also equal to 1. Right? So apparently this is corresponding to this point. The eraser doesn't work that well in Zoom. So let me draw it. Both true positive rate and false positive rate are probabilities, so both of them are bounded. So this point is 1, 1. Right? True positive rate is 1. False positive rate is also 1. So in this case, it is this extreme case, theta is equal to 0. Right? And if false positive rate is 1, that means true negative rate is 0. Right? So this is one extreme case. Right? True positive rate is 1, true negative rate is 0. Right? Now consider another case if theta is equal to 1. In this case, all the predicted values will be negative. Consequently, probability of negative given negative will be 1. And probability of, let's consider the positive case only, because the two values in the ROC curve are all about positive. Then probability of positive given positive will be equal to 0, right? Because it's not possible to predict the positive value at all, right? And at the same time, probability of positive given negative is also equal to 0. Is that right? Right. So true positive rate is 0 and false positive rate is also 0. Right? So which is apparently corresponding to this point. Right? This point. 0, 0. Yeah. So yeah. And false positive rate is equal to 0, which means true negative rate is equal to 1. So at least one of them is good, okay? So one good, one bad. Similar here, one good, one bad, right? One is the best, one is the worst, okay? So two extreme cases corresponding to two extreme cases for theta, the threshold, right? And anywhere in between will be some model that will have a non-zero true positive and non-zero true negative. Right? And now consider this point. This point. At this point, let's see what happens. Right? So true. Let's see. Oh, sorry. I draw it in the wrong way. That's why. Um, the x-axis should be corresponding to false positive rate, and the y-axis should be corresponding to true positive rate. Let's see. Draw it again. It's a little bit tricky. Okay. So this is, let's see, theta is equal to the true positive is 1, false true positive is 1 equal to 0. This is the same. So this is theta equals 1 case still. Okay. All right. So this is true positive rate is 1. False positive rate is 1. Which means true negative rate is 0. Now here is true positive rate is 0. False positive rate is 0, which means true negative rate is 1. All right. Sorry about that. I should be more careful. And now let's consider this point, right? Let's use a different color. So true positive rate is 1. This is good. And then false positive rate is 0 at this point. Consequently, true negative rate is equal to 1. So this is the ideal point when true positive rate and true negative rate are both equal to 1, which is the ideal case. Unfortunately, as I said, it never happens. Right? You can try to approach this point, but it will never happen. So a typical ROC curve will look like this. And the closer the curve is to this point, the ideal point, the better the model, overall model. So consequently, the larger the area under the curve, the better the model in general. So this area is just called AUC, right? Area under the curve. Right? So the larger the better, usually. Right? And because this one, the ROC curve considers all of the possible threshold from 0 to 1. Right? It provides a comprehensive metric for evaluating a model and also for comparing different models. Right? All right, so now we're ready to see how to create ROC curves. Your textbook uses this package, ROCR package. There are a few steps before we can plot the ROC curve by ourselves. So first, we need to calculate the class probabilities for the test set. So notice that we let type equals prob, which means we choose to return class probabilities instead of class labels. So usually this is a type equals class, then it will predict the label. For example, for the first observation, it will return Clinton. The second, it will be Obama, okay, etc. But we will use this predicted probabilities in order to calculate the ROC curve. So we choose to return probabilities, okay? So this save the result here as a data frame. You see two columns. One is the winning probability for Clinton, and the other column is the winning probability for Obama. Of course, the sum of them is equal to 1. Right? We call it win prob RF. And then there is a function in ROCR, which is called the prediction function. So this one will transform the input data into a standardized format. It takes two basic arguments, predictions and labels. The predictions is the class probability for one class. And then the labels is the true predicted value for, basically the Y test, right, the column. So let's first predict labels first. Right? We still need the labels. So we use the predict function to predict the labels for the test set, call it predict RF. Notice that is different from this one. Right? This one is a data matrix of two columns. This one is just a vector of predicted labels. And then we apply the prediction function on the winning probabilities for Obama. You see the second column. And then the label, the true label, okay, not the predicted label. And save it here. Predict RF prob. And then one more step to calculate true positive rate and true false positive rate and true positive rate. That is for the ROC curve. Right? The function is called performance. You need to provide a few terms: prediction object, measure, and X measure. Prediction object is an object of class prediction. So in our case, is the probability of the winner is Obama. Okay, so this one we calculated earlier. Okay. And then measure. So this is a performance measure used for the evaluation, and X measure is a second performance measure. So this is actually the Y-axis in the ROC curve, which is true positive rate. And the false positive rate is the X-axis. Okay. And then we're almost ready. Make it a data frame and add column names, false positive, true positive. Okay, so these are the first three rows of this object. Okay. So a column of false positive rate and column of true positive rate. So this is the X in the ROC curve. This is the Y in the ROC curve. And then let's create the ROC curve for random forest, for our random forest model. It looks like this. It considers all of the threshold from 0 to 1. Okay, so the curve is trying to approach this ideal point, but it can never touch it. Okay? And this point is a model we actually fitted using the default threshold 0.5. It must be on the ROC curve. And this area is the area under the curve. You see for the random forest is quite large. Right? It's almost a square. Right? The area is almost like a square. Okay. So this is how we do it using, so this is the ROC curve for random forest. For comparison purpose, we can do the same thing for the naive Bayes model. Right? Basically, you have to go through all the processes the whole process of preparing the data for the ROC curve and just add a new layer of line and point into this plot. So this purple one is corresponding to the naive Bayes model, and the orange one is still the random forest. So apparently, the random forest model is superior than the naive Bayes model, no matter what threshold we choose. Right? The curve is always above the naive Bayes model. Right? There is a big difference between these two models. So this is one extreme case because the naive Bayes model is the worst and the random forest model is the best. So they don't cross. But sometimes you may see ROC curves that cross with each other, right? Somehow like this. It's possible. With a different threshold, they may have different performance. All right. So this is how we use the ROCR package. And I think yet another way, which is another way that it is easier. Okay, so this is the PROC package. So this package is much easier to use because we don't need to calculate those true positive rates, false positive rates by ourselves. You just need to provide something. Right? So load the package, and the function is just called ROC. And you still need to provide the true labels in the test set, and also the winning probability for Obama, in our case, Obama. Right? So this one, you still need to calculate first, right? And then feed it into the function. Okay, there are some arguments. For example, CI, confidence interval alpha. Okay, this is actually a 90% interval. So, and also stratified plot. Yeah. So you can play with these hyperparameters in the function anyway, and then calculate the standard error and plot the result. So this is an ROC curve for the random forest. Yeah, I think. No, sorry, this is for the naive Bayes, C and B, naive Bayes. So it automatically calculate area under the curve for you, like 0.831. Okay? The maximum is 1. 1 times 1 is 1. Right? So 0.831 is already pretty good. And it also calculates the 90% comfortable for you. So this is 0.794 is corresponding to this area. Okay? And 0.868 is corresponding to the biggest area. Okay? Well, I think it's 90% because I chose to use 90%. And this is naive Bayes model. How about the random forest? You see the area under the curve is 0.946. It's much bigger. Okay. And the confidence interval is between 0.927 to 0.965. And a drawback is you cannot put the two curves in one plot. Right? I don't think there is that option. However, you can still make conclusion about the best model because you see the lower limit of the ROC of the AUC for random forest, which is 0.927, okay, is higher than the upper limit of the AUC for the naive Bayes model. The upper limit is 0.868, right? So this means the random forest model is significantly better than the naive Bayes model. And it's always better, almost always better. But comparing the area under the curve. So of course you can do both, right? Because this one allows you to compare their ROC curve at the same time to see if they if one model is better than the other always or sometimes. Right? And this one can help us to to make conclusion in a more concrete way because you can say, okay, we are 90% confidence that the naive Bayes model is worse than the random forest model, somehow like that, right? Because yeah, we have their confidence interval information for AOC.